we are starting ahead of time or what?
So usually, sir, last time, once it happened that there was some time gap. We got little late while going on that YouTube thing.
Okay. In any case, when we go live, we are not starting before 11, right?
No, no, sir, no, sir.
Perfect. Perfect. Go ahead.
So Krishna, should we mute ourselves? Okay, live streaming started. So good morning, everyone. A very warm welcome to the ninth session of Semiconductor Nation Campus Connect webinar series, which is an initiative under Semicon India Future Skills by ISA. So under this series, our intention is to cover the journey of the SAN to electronic systems, how the things start. So the picture, the slide which we are sharing here, it's giving you all a global overview of this journey, and what are the things that are covered during the course of this journey. So in this series, we are intended to cover one block at a time with the intention to give the students an overview of how it starts with the SAN and how they have any electronic product in their hand. So the previous sessions are recorded and they are archived on ISA's YouTube channel. And this session will also be recorded and will be made available to everyone to access it freely anytime they want. These sessions can also be used by the faculties as a part of their lecture as and when it is suitable during the course. And also, since we have moved to the weekdays now, our one more intention is that these sessions can be live streamed by the faculties and the colleges for the students. And also, we request you to post your questions, your queries, your thoughts on the chat box, which will be discussed towards the end of the session. In the last session, there was a discussion that happened towards industrial safety for semiconductors and display. This session, the speakers will be talking about the physical design, RTL2GDS flow overview. So with that, I'll introduce you all to our speakers for today, Mr. Sai Narayanan KS and Mr. Roshan Kumar. Mr. Sai Narayanan is currently working for Marble Technology as a CAD director, driving India Center CAD and Methodology team, and he has around 18 plus years of experience. He also spearheads the static timing analysis and part integrity CAD flows for Marvel worldwide. He has authored 25 plus papers, and he holds MS Research from IIIT Hyderabad and BE in Electronics and Communication from Madras University. Our second speaker for today is Mr. Roshan Kumar, who is currently associated with Marvel Technology as Senior Manager, and he has 14 plus years of experience. His core expertise is physical design domain, and he has authored 10 plus papers. He holds BTech in Electronics and Communication from NIT Jamshedpur. So thank you, Sai, thank you, Roshan, for joining us, and over to both of you.
Okay. Thanks a lot, Shushma, for the introduction. So today's topic for the webinar is RTL2GDS2 flow overview, right? And firstly, right, I'd like to, thank for the opportunity to present at IESA, and it's great to also, IESA is playing an instrumental role in making sure that a lot of colleges are getting benefited and exposed towards various aspects of electronic design as such. Right. I just want to give a quick overview of today, right? We're going to start with what is physical design, all right? And I'll be touching upon some of the back-end design flow, right? Complete detail from RTL to GDS, right? Various steps involved, like all the way from flow planning, routing, right? We're going to kind of touch upon that. We'll also give a glimpse on sign-off flow. What are the various sign-off flows, like the static timing analysis, power integrity sign-off, or a PV closure, a physical verification closure. We're going to touch upon that in the sign-off flow, right? And we're also going to touch upon and give a glimpse on left shift mindset, right? Just to give a brief of what exactly the evolution of physical design flow has been, right? There have been a lot of evolutions from the automated physical place and route flow. So we're going to kind of give a little bit of glimpse of what is there in the current trends which is happening in the industry as such, and at the end we'll wrap it up and open up for Q&A. So before I begin the talk, this slide is a beautiful slide from IESA, which talks about Santo electronic system. There have been prior talks, some of them, I guess Pradeep Thakur started with the talk on ESDM, which is out there, he was talking about system design, manufacturing, and electronic stuff, right? And there were also seminars, webinars, which were there on touching upon some of the aspects of verification in the past. So in this webinar, our focus would be on a physical design, which is the design layout, and currently we have tools for doing it called EDA tools. EDA stands for Electronic Design Automation, and I'll be covering through a little bit more details on that as well. In addition to that, you may also want to observe that the physical design is a stage. After we do the physical design, it gets into fabrication, right? When you say fabrication, it gets into a foundry where they manufacture this as such. So physical design is a bridge between, if you look at it from the logical to the fab, whatever you do physically, right, is what is called as physical design. Furthermore, steps are down. If you look at it, the job is not just done with physical design. You have, fabrication happening. After that, you have wafer, right? You need to kind of do a lot of testing and whatnot. And at the end, right, we have to kind of assemble, and it goes as a product as such. So much of, steps are involved as such. So firstly, what is physical design? So physical design in, very 50,000 feet of view. If you look at it, it's like translating an higher level language to something which is manufacturable or which is a layout as such, right? In this case, typically the languages which we use is like, we call it as register transfer logic, or called as RTL, right? Left side is one of the formats called, one of the languages called Verilog, which is used. And you also have, VHDL, which you could also kind of elaborate for RTL as such, right? So this coding, right, whatever you have on the left side, is just a example of a multiplier instantiating full adders and the half adders out there, right? Translating this logic which you have written, right, to something as a layout is what is called as physical design, right? And you may also want to understand that typically the RTL is technology independent. What I mean is there is no technology involved in RTL. It's basically, as you could see, left side is a description of the circuitry as such. The right side, the layout, right? When we translate it, we are translating to something which is more technology focused. When I say technology focused, let's say you have a 16 nanometer process, right? You have a 5 nanometer process. The 5 nanometer represents the channel length for a particular gate as such, right? And it is like process, and it's also pertaining to a manufacturing company. For example, there are multiple foundries. We call them as foundries. There are multiple foundries like TSMC, Taiwan, semiconductor manufacturing company. You have something like SMIC, which is there, based out in China. You have UMC, which is also there. You have Samsung, right? And Intel recently as well, right? So we call them as foundry. So they are like manufacturing firms, right? So we kind of give the blueprint. Layout is like a blueprint. You send it to a foundry, right? And then they kind of manufacture them. This blueprint design is what is called as physical design. You can think physical design as an analogy to civil engineering, right? So effectively, what you do in terms of an house is to, you have some kind of, some idea which is there, right? And after that, you kind of floor plan, you decide upon where you need to place, certain things. For example, right, you want to have a kitchen on this side of your, floor plan. You want to have a dining room at this side of the floor plan, right? So all of this is, is literally a floor planning, which we call in civil engineering. By the way, the same terminology is also used in chip design. It's also called as floor plan, right? We literally make sure that, things are placed as what is expected. And you could also see that, similar to channels which we have, you also in civil engineering, you are connecting certain things, beams and whatnot. The same thing you can analogize to, you could have it to, metals connecting as such, right? So in short, if you look at it, it's almost like civil engineering, except for, we call it as, if you put it in a layman's language, what is physical design is, it's nothing but civil engineering on a chip. So before I jump into, automatic place and route, or RTL2GDS2, I want to give a glimpse of what physical design approaches are present. Typically, what happens is that whenever we talk about physical design, people immediately latch on to RTL2GDS flow, which is more, furthermore, more an automated process. But physical design, as I told you, is nothing but something before manufacturing step is what is called physical design. So there are multiple approaches. One is the custom design approach, right? Typically, some of the analog designs are very, very sensitive, right? And for example, you need to match certain things. For example, a current mirror, which is out there, you need to make sure that the layouts are well matched, right? So it needs literally someone and drawing. There are, obviously, you can automate to an extent, but automation is not all about in analog design, right? Because you're the pre-parasitic versus post-parasitic simulation is very, very complex in the case of analog design as such. So people typically hand draw them. This is what is called as custom. So as the name represents custom, right? And people are literally hand drawing, right? The other one approach is the semi-custom approach. Certain designs are there wherein portions of the designs are very critical. For example, let's say you take a processor, the L1 cache interfaces are very, very critical typically. So you kind of handcraft them. You kind of, manually place those designs, those portions of the designs alone, and then craft them manually or, do them. The rest of them are a little bit more automated as such. This is what is called a semi-custom design. The third one, which is a topic of interest for today, is the automatic place and route, right? The reason we call it as automatic place and route is the design sizes are very, very big. Let's say you have, millions of instances, billions of instances in the design, for example, right? So you can't manually place them, right? So when you start placing them, obviously you can do that, but it's going to take ages and ages of time to kind of perform such kind of task, right? So in order to do this repeated task, right, invent of algorithms came into picture, right? These algorithms have been, either in the past, there were companies designing their own algorithms for doing it. And there have been EDA teams in each and every big organizations which were there. Now there are specific companies and vendors called EDA vendors, called electronic design automation. As the name suggests, it's a one which incorporates all of these algorithms to kind of handle very big complex designs for being placement or being clock tree and whatnot, right? And these algorithms are cost driven. What I mean is, depending upon the cost function, because these are algorithms, you need to have a definitive endpoints. So you need to make sure that there is an optimization cost functions for these problems. Otherwise, the solution rate is pretty big and the algorithms may not converge in time as well, right? So there are various cost functions which has been involved, like the performance, power, and area, which I'm going to discuss a little bit more in detail, right? So effectively, that's what automatic place and route is actually, right? Call it APR. And typically people call this as RTL2GDS2 flow. They refer to, APR with tools, using tools as such. So this, in this webinar, we are going to be focused on touching upon, the automatic place and route session as such. So before I dive into details of, the RTL2GDS2 flow, I want to give a glimpse of what's upward and what is downward as such compared to what place and route is happening as such, right? Initially, we have, before a particular product which has been designed, there is something called, an MRD document called as marketing, requirement document, where the marketing team goes and figures out what is the product which needs to be done for a market segment as such. And that MRD document gets translated to something called a PRD document called as product requirement document, where you literally, spec that through in terms of what is the requirement for the product. And this becomes like the seed for engineering specification as such. And post that, we design the architecture for this product, right? So you kind of design the architecture. So architecture as such is very common. For example, you have an x86 architecture, right? The architecture is x86, but you have Intel, manufacturing them and also AMD manufacturing them. But the architecture remains the same, which is x86, right? The implementations are different. The implementation difference is what is called as microarchitecture, right? And that could be really different. And you could innovate in the microarchitecture space to make sure that, it could be much better than, your competitors for a particular architecture as such. So that translation of microarchitecture we do through RTL design. That's the first step which happens. And there is also verification which happens, wherein you kind of verify what is written in the RTL. Post that step is DFT. DFT is very, very important. Design for testability. So focus on design for testability. Is make sure that there are any manufacturing defects which are there, right? You kind of make sure that you figure that out post manufacturing, right? What kind of issues are there? In order to figure that out, we need to insert certain things upfront, pre-silicon. Like, for example, if a memory is there, you want to insert something called an MBIS, called as memory bus, built-in self-test, to make sure that memory is functioning properly when it boots up really after manufacturing. The importance of this is well known. For example, if you have automobile sector and you don't want your ADAS to stop working when suddenly there is someone coming and going to bump up and crash through, right? So DFT is very, very important, right? In such kind of scenarios, you make sure that your circuitry is working absolutely properly. There are techniques like redundancy added in just to ensure that the safety, right? Especially, I guess there was a previous lecture on the webinar on functional safety as well, right? Industrial safety. Here also safety is very important. So we create something called redundancy in the system to make sure that's been ensured of. Post that, we have synthesis. Synthesis is promptly a translation from what you have as an RTL to a technology-specific netlist, right? When I say I'm stressing on the word technology-specific, Roshan is going to cover a little bit more detail on it. When I say technology-specific netlist means a particular technology. AND gate is a generic gate, right? When I say technology, the layout for an AND gate would be different between a 5 nanometer versus 16 nanometer for sure, right? And even the characteristics are different. So when I say technology specific, you decide on a particular technology, let's say a 5 nanometer, you're manufacturing, you're converting the RTL to a netlist, which is technology specific. That is synthesis. And we also have the logical equivalence check, where you compare whatever you have written in the RTL is the same as what you have in the netlist. Post that is place and route, which I'm going to cover in detail. On the sign-off flow, which is very, very important, we are also going to touch upon various aspects. Before you kind of manufacture, you want to make sure that each and every aspects of the chips have been tested across. Because manufacturing is very costly, right? Any bug, which is unlike software engineering, right, wherein you could kind of patch it through software updates and whatnot. Right, hardware bugs, you need to kind of do respins of it. You have to do a metal tape out on them in certain cases, or completely, a redesign in certain cases as well, incremental redesigns, right? So you want to avoid those kind of cost in dollars. So we call it as, the best design practice is to have something from A0 to production, right? You want to make sure that the production is first time you manufacture absolutely great. So to ensure that a lot of the sanity checks and sign off has been done. And finally is chip finishing, a step, wherein you ensure before getting to the foundry all of the manufacturing details, right? Because at the end of the day, in foundry, you have manufacturing equipments which has some limitations on stepper sizes and whatnot, right? And effectively just gets translated into DRC rules, which I will be covering a little bit detailed during the sign off. So all of this have to be taken care before we kind of pass it on. So coming to the topic of interest for today, right? The place and route, if you look at it, I'm going to go really quick at the moment and then cover on the next slide, which is for the more detail. So we have the design import phase where you kind of import the design. You do the floor planning where you kind of make sure that, some of the memories, some of the IOs, everything has been placed, right? Power planning, right? Similar to what you do for your house, where you kind of make sure that electricity is being sent across all of your rooms, right? The same thing is power planning is ensuring that making sure that all of your cells are getting power from the power source so that they behave, what as expected. The placement is like you kind of place them through, right? In this case, it's an automated placement. So floor planning is placing bigger blocks, and placement is like placing some of the, cells called standard cells, which Roshan is going to cover a little bit more detail with an automated fashion because the instance counts are pretty high, right? And we also do a pre-CTS optimization using all this high fan-out synthesis and whatnot, and then route and post-route. The key metrics for all of this is PP and A, right? You heard this, you hear this acronym pretty often, right? Which is like power, performance, and area, right? These three are very, very key metric, right? In any of the optimization problem which is being dealt in, right? And you're going to change depending upon when you're going for a performance optimized design. The way of optimization will be quite different than you focus for performance and area as such. So let me dive to this, highly content page wherein I kind of put in a lot of them, but each and every topic is going to be presented in detail by Roshan in the subsequent slides, right? So I'm going to give a glimpse of, each and every step, and then I will hand it over to Roshan, right? So synthesis, as I early mentioned, right, it's an RTL2 gate. Typically you have RTL, you kind of convert them into a technology specific gate level netlist. This is called as logic transformation. A very, very important step here, right? Because depending upon, as I was mentioning to you, the PPA, let's say you want to optimize on performance, right? Let's say you have a, adder which is out there. So the selection of adder, right? You could have, ripple carry adder versus, a carry locator adder versus something like a cockstone adder, which is much more high speed, right? So depending upon your performance versus power trade-off, area trade-off, you could select architectures for adders, right? And same with respect to multipliers, for example. You can have a Baguli multiplier, right? Or a Valastri multiplier, right? You could select all of these happens. We call it as logic architectural selection, right? Which happens during synthesis by looking at the way in which the RTL is coded. Let's say you put an A star B, right? What kind of multipliers do you pick for, right? So those kind of things are being, done during synthesis, where you literally look at what kind of data path architectures to be selected. There are, which is really based on PPA. There are techniques like register retiming, like you kind of borrow certain logics, right, from one side of your reg to reg. And typically, if you look at your, a design, it's a pipeline system. You have registers, you have logic. Again, you have a register, you have a logic, and that way, right? Let's say the way in which you code, sometimes what happens is there are imbalances, in the way in which it is being coded. And it could lead to performance bottlenecks in certain cases. So what we need to do is you borrow a certain set of logics from one side of your register to the other side of a reg to reg, right? Making sure that your logic is well balanced to an extent and improve upon performance. That is register retiming as such, right? And also we have DFT is one of the major step out here as well. So all the flops which are there has been converted to a scannable flops, and you stitch them through something called a scan chain, right? Where you kind of stitch them through. And after, there are tests like ATPG to kind of make sure that you get patterns. Post manufacturing, you kind of test it through those patterns, making sure that it's adhering to, all the tests are clean and there is no any manufacturing defects as such. So post that, it's an handoff, right? It's called as design import step. This is an handoff to physical design world, where you have a logical netlist which is out there, and a lot of other which is called as Verilog, which I put as an input as Verilog. There are other formats like UPF, which is called as Unified Power Format, where you kind of define some of power requirements. And also, when I say power requirements, I mean sometimes you have various domains in your design, right? So let's say that you don't want depending upon your application, right? You don't want all of your logics to be running at the same high voltage, right? To save power, some of them could be running at a little bit of lower voltage. For example, you have a peripheral versus CPU, right? The peripheral, you do not run peripherals at the same high speed as what you do for, CPUs as such, right? So effectively, you can lower some of the voltage out there and save power, right? So all of this is being captured in an IEEE format called, UPF, Unified Power Format. So all of them are standards out here, so that, right, all the EDA vendors consume similar kind of format. So standardization really helps, right? All these IEEE standards, and the standardization is the key to make sure that various companies work with the same inputs. And we also have, libs, which is a liberty, where you have all these standard cells characterized, and, even memories, you have the dot libs, you have timing, power, everything captured, noise captured in the dot libs. And post that, we also have the constraint, SDC, which is the timing constraint of how much frequency you want your design to be operated on, right? So that's basically the cost function for the optimizations engine as such. So that's the design import stage, and floor planning and power grid planning, right? So where we define the die dimensions. In the case of floor planning, as I earlier mentioned, you figure out how much is the dimensions which is out there. Where do you want to place these memories, IPs, and whatnot? What are the physical constraints like fences, regions? Similar to literally, you have a house and you want to barricade completely with a complete concrete wall, right? It's like fence, right? You basically make sure that you're just pertaining all the cells in a particular region, right? There is no cells coming out of the region, and no one is also involved inside, right? It's more like literally like barricade. That is fence. Region is still the cells will sit right? Whatever is the logic will sit inside the region, but you also allow, there are spaces out there, right? You could also allow people from outside cells to other logic to sit inside, right? So these are just terminologies. So that's why it's called a physical constraint, right? How do you play? And there are like blockages, partial blockages and whatnot, right? And also we have this chip finishing cells, like all this well taps. So for example, the taps, right? You would have surely learned about latch up rules, which are there, right? So wherein you have a latch up if you don't bias your substrate properly, right? So well tap kind of, helps in kind of making sure that there is a uniform, tapping which happens, right? Because all of these standard cells are tapless libraries, and through well tap, it gets connected. And typically around like 50 micron distance, these well taps are there. And it's been dictated by the foundry, depending upon how much is your substrate resistance, right? And you also have this macro grids, and which specifically for memories, you want to make sure that you power them up in a different fashion because these are pretty big, right? And post that, we have the placement and optimization. The major aim of placement and optimization is wire length reduction. You want to make sure that wire length is well reduced, right? It looks at various cost functions like performance, power, congestion, right? Like similar to what you do, you have very big, big spaces out there, but your channel is very small, right? In your house, it's going to be really tough for people to walk through, right? So you want to make sure the channel is also given. Same with respect to physical design out here, right? If you have, a lot of cells out there, you need to make sure the channels are being given, or, route tracks are present, ensure that routing happens to these standard cells. CTS, clock tree synthesis, is out of the system, which is a spine of the complete, sequential design as such, right? You want to make sure that all of your clocks and each of your flops or flip-flops or registers are with adhering to some spec, like they are coming at a right amount of time, right? So we have various terminologies like skew out here, right? Latencies out here, which Roshan is going to cover. You want to make sure they ensure that all of them are arriving at the same time, right? The difference between arrival times is called skew. You could have like global skew, local skew, various definitions. Now, I don't want to bombard you with a lot of, various definitions as such. But, in short, if you look at it, you want to make sure that, the clock reaches each of the flip-flops at certain amount of time. So in order to do that, there are a lot of terminologies like X tree, H tree, mesh, right, and whatnot. And this contributes to dynamic power, right? Clock is always switching. So there are mechanisms like clock tree gating, right? So we call it as clock cells, which are there in the standard cells to gate the design in case if your logic is not operating as such. And post that, we have the route and post optimization step. Routing is nothing but connecting, the logical cells, right, which are being placed using a wire segment. This is real physical design, right? Basically, you're placing them and you're routing them, right? Wherein you connect pins with wire segments, right? And depending upon number of layers, right? A foundry could have like 16 layers, 8 layers. So that means that 8 layers are available for you to route. 16 layers are available for you to route, right? And it's been connected to through something called via, as the name suggests, right? Via, right? So via this, right? We call it as via this route, right? So via is a connection between two metal layers as such, right? Which happens. A lot of other steps, we have separate slides for each of them, and Roshan is going to cover them, where we have detailed routing and DRC, which happens as well. Right? And with this, I'm Roshan, over to you.
Thank you, Sahil. Hey everyone. First of all, thanks to IESA for providing the opportunity to present over here. And I think Sai has given a very brief but detailed start to what is going to come next. And the previous slide actually had a lot of information regarding the steps which are going to come now. And starting with synthesis, right? Primarily, synthesis has been a logical step. As Sai mentioned as well, this is where you're converting your logical RTL to the physical side of the design, which is the gate level netlist. If you look at the flowchart on the right, you have an RTL, and what you get out of synthesis is a technology specific netlist. What we need to understand is what is technology specific netlist, and also what are the constraints which are driving this technology specific netlist. Right? If you see on the right hand side, you have various constraints which are guiding how or what your netlist is going to be. Some of the constraints which are timing constraints. There could be power constraints as to how much power your design can have. There could be some more constraints depending on the design, right? And on the left hand side, you have technology library file. These are technology specific library files. say a 5 nanometer technology or a 14 nanometer technology, and so on and so forth. So basically, you take RTL, which is technology agnostic, which is written in a hardware language. It could be Verilog, it could be VHDL, and you convert it into a gate level netlist, which is technology specific. And the steps, well, there are various steps. Initially, you map this RTL to some generic gates. Say if it is a NAND gate or NOR gate or inverter or buffer, you just translate them to the specific gates as such. Depending on the constraints which you have in your design, then the specific gates starts getting picked up. Say you have a very tighter constraint on area, a very tighter constraint on power, then so and so gate would be selected. And then you have technology specific constraint as well, that you want to get your netlist in a 5 nanometer technology or in a 14 nanometer technology. So then the specific gate would be selected. Once this is done, what you get is a gate level netlist, which is the initial handoff file to your place and route person. So this is the file which a place and route person would take and then proceed with his further steps. Yeah. So coming to floor planning. So before floor planning, what we have is a partitioning. Partitioning is nothing but a precursor to floor planning. If you see, right, on the right hand side, you have a chip, and this chip is say nowadays it's quite big in size. In fact, it is becoming bigger and bigger. So one cannot run the flat full chip as such, because the design has millions or billions of gates and transistors, right? So partitioning is something where we are actually dividing and concurring the design. And the division also happens with respect to certain guidelines. So if you see, right, various partitions can be of various shapes and sizes, and the shape and size again depends on what is the logic content of that partition, what is the power constraint which is guiding that partition, what is the area constraint which is guiding that partition, and so on and so forth. Depending on all of this, you come up with the shape of the partition. And then all these partitions can be run in parallel. They will be independently assigned to various team or engineers, group of people, and they then can run everything in parallel, which kind of helps us converge faster for a given date, because time to market is important, right? Once all these partitions run in parallel, end of the day, everything has to be signed off flat. So you don't want to sign off everything one by one and then say that, hey, my design is ready. You obviously have to assemble everything. And once everything is assembled, for the sign off phase, you definitely have to run flat. For the implementation, you were not running flat, you were running in parallel. But for the sign off, majority of the things will get sequential, and everything will be run at once in a flat run. Yeah. So deep diving into partition floor planning, right? So if you see on the right hand side, we have taken example of one partition, partition one to say so. Uh, as Sai mentioned, right? Floor planning is nothing but a physical designing of the chip. Physically, we were designing our house or our rooms as such. On the right hand side, what you see is big blocks of macros. They could be memories. So the netlist, the gate level netlist which we got, right? The gate level netlist can have standard cells. We'll see what standard cell is. It can have specific IPs, say a memory. It can have an IP like a PLL, an IO, and whatnot. So all these big blocks needs to be arranged in a proper way, so that you have ample space for your cells which are coming later in the design to be placed. And if you see, right, they are also, these logics are also grouped. So you want to make sure that the specific group or a particular group sits in a particular corner or particular place in the design. You don't want these big blocks to be placed randomly. Say for example, we have big blocks in our houses, right, in our rooms, the beds, the tables, the almirahs and whatnot. You want them to be placed in certain corners, so that the alleys and the foyers are kind of they have ample space. So This is where the big blocks will be placed. This is one of the first steps in design execution. So it's very important that we get this right. So a good versus a bad floor plan can make or break things. If I am not placing my design, not floor planning my design properly, then obviously the subsequent steps are going to have consequences. The consequences could be higher area, where I'm not able to accommodate what is given to me in the given area. So I need bigger area. It could lead to congestion because I only have so much area or so many tracks to route the logic, and I'm not able to do because my floor plan is not proper. It can lead to higher power because my design was not floor planned properly. Now I need more cells to meet the same PPA guideline, which means more power, right? And it could also lead to timing challenges. If this was a chip level design, this is currently a partition. If this was a chip level design, then it would also contain other important IPs like the analog IPs, the PLLs, and as such, and the IOs, which are helping us talk to the outside world. It's very important to have a design understanding to have a good floor plan. Yeah. Yeah. So coming to the power plan, right? So my design is synthesized. I have partitioned my design. I have also floor planned my design. Now it's very important that my design has the power meshes and whatnot. Power mesh is very important. First of all, every part of the design needs power, so I need to have a mesh. Secondly, mesh helps us reduce the resistance. We know, right? Resistance always reduces in parallel. So this is what exactly is happening over here. You would see that straps are drawn all across the design, and they'll be in vertical as well as horizontal directions. And primarily there would be VDD and VSS straps. There could be some more straps depending on what is the power topology of the design, what is the power requirement and constraint of the design, right? It's important that the straps are routed in higher layers. So a design can have a number of layers, starting from layer 1 to layer 10, layer 15. It depends on the technology, it depends on the design requirements, right? And as you go higher in the layers, the resistance of that specific layer reduces because the width of the wire drawn can be more, and the thickness of the wires drawn in those layers are also more. So effectively your resistance is reducing. uh, for power, it is very important that we meet certain guidelines, say the guidelines like IR drop or voltage drop in the design, the guidelines like electromigration. These needs to be maintained. For that, we always try to get our powers in higher layers because they provide us lesser resistance. At the same time, while we are trying to get as many straps or routes in higher layers as possible, it is important that some of the layers are also, you know, saved for the later steps which are going to come in the design. So it's kind of a trade-off between what your power is versus what your later stages are going to come. If this was a chip level, then it would also contain the power pads from where the inputs are coming from outside world, and it would also contain what we call as bumps. Bumps are basically locations where the powers are directly coming from the outside world. If you remember the flip chip versus the wire bond, right? So flip chips are basically bumps based. Yeah. So now our design is floor planned as well as power planned. So the next logical step is to get the standard cells in the design. Now, what is standard cell and why they are called standard? Standard cells are nothing but basically logic gates and NOR, buffers, inverters, whatnot. They were always there in our netlist right from the synthesis stage, but they were not placed in the core area. So in the previous snapshots, you could see these big blocks, but these small boxes, these squares and the rectangles, they were not present. These are the standard cells which are placed in the core area in the placement stage. Now, if you see, right, it was very important for us to leave some vacant areas such that the corresponding standard cell or the corresponding logic which talks to that big macros or the big blocks, they come and get placed. They have ample space, right? So they should be placed in optimal way. It's very important that the standard cells are placed in optimal way and they have legal locations. So if you see, right, they are placed between those two lines. Those two lines is what we call a standard row. So the height of these rows are defined. They can only be in integer multiples, and the width also is defined to be certain integer multiple, and hence they are called standard cells. So one can only go in certain integer multiples in the height and the width, and hence the name standard cells, right? This is the first level of optimization after the placement of the design. So this is where heavy optimization is going to happen. The high fan out nets, say a design which has a reset signal. Now, a reset signal could be a very global signal. So the reset signal is going to reach all the logic in the design, right? So that will have a huge fan out cone. So you really need to kind of strike it down here itself, optimize all those such high fan out net cells. There could be downsizing and upsizing of the gates which are there. There could be inverter buffer addition and so on and so forth. While doing so, it is very important that we keep the PPA of the design in mind, the timing, the power, and the area consideration, as well as the congestion. You want to make sure your design has lesser congestion, because some more cells are going to come at later time, and physical routes are yet to happen. As of now, we only have the estimated routes in the design, which will slowly turn into real routes as we progress with the further steps. Yeah, so my design is floor planned. I have placed my logic in the design. I have also optimized my logic in the design, and the optimization happened on the data side. Now comes the step where the optimization should also happen on the clock side, because my entire design runs at a certain frequency at a certain clock period, right? So clock tree synthesis is a very important step, because this is where the clock which is going to the entire design is going to get the CTS structure is getting built, and the optimization on both the clock as well as on the data side will happen here. So if you see, the clock will be distributed across the design to all the sequential part of the design. And it is very important that I have a common clock path. So if you see, right, if you see a tree, let's take an example of a tree. A tree has a trunk which is common to the entire tree, and then it has branches, and then it has leaves and whatnot. So the common path helps reduce the variation in my design, specifically in the clock path. The clock also needs to be balanced. If you remember, the rise and fall times are different for both the FETs which are there in the design. So it is very important for us to have equal rise and fall time, so that my clock period which is there is maintained. To maintain that equal rise and fall times, which we have specific cells which are created for that. So these are called as balanced cells, the balanced inverters and buffers. So we are going to use balanced cells to create our clock tree structure. We need to make sure our delays are minimum. Delays here could be the skew and latency. Skew is nothing but the delay difference between two sequential elements, say two flip-flops which are talking to each other through a data path. The clock arrival time between the two flops needs to be within certain guidelines, certain constraints, so that the timing is taken care of. Similarly, if my design is not active, certain part of my design is not active, right, for whatever reason, be it technical, then I don't need that portion of my design to be active. For that, what we would do is we can shut off that logic by adding clock gates in the design. There are multiple CTS topologies which can be used. The H trees, the mesh, the X trees, which was mentioned by Sai in the previous slide. H is a common one which is mentioned in the snapshot over here. If you see, right, it kind of forms a H, which looks like a tree where there is a main trunk which is coming from the clock root, and then you have signals going in various directions, which again forms an edge. This kind of keeps the balance in the clock structure and helps meet the arrival times of respective flops. While you are doing the optimization, right, again you need to consider the PPA of the design, the performance, the power, the area, as well as you need to make sure the skew and the latency of the design is within the limits of what we started with. Yeah, so my design now reaches the routing stage where the data routing, the signals which are on the data side will be routed. So till CTS, I made sure my clock tree structure is final, my clock tree cells are there, my clock tree is routed, all those things were taken care. Now comes the routing part for the data nets. So if you see, right, basically routing is the step where we are physically connecting the pins in the design, the data side of the pins, using metal wires. And if you see on the right hand side, we have a step what is called as global routing, and then we have something which is called as detailed routing. In the global routing stage, right, the design is going to be bifurcated into smaller chunks. The entire design cannot be routed or estimated at once. So here the tool, the EDA tool, will divide the design into multiple small boxes, and it would try to estimate routes through those boxes. It would do an estimation which is called as global routing. It would also do track assignment for all those nets which are running through those boxes. Then it would do layer assignment, so we know where the net would go. We also know what would be the topology of the net or physical wire. Then we get to know what, for that topology, which specific metal wire, which specific route to take to reach that. And then we perform the actual routing. So global routing is what we had till now in the design, where estimation based routing was there when we were doing all these steps of floor planning, placement, pre-CTS optimization. This is where the actual routing happens. And once you do the detailed routing is where you have actually routed the design. So if you see the below snapshot where you have the horizontal wires and the vertical wires, you also see some small boxes in between over there. These boxes are nothing but the wires in the design. So wires are basically the components which are connecting your orthogonal signals. The routes in the design are going in two directions, horizontal and verticals. Now wires themselves can be of multiple types. They can be a single cut wire. There can be a multi-cut wire which further increases or improves your reliability of the design. There can be some more types of wires, the wire ladders and whatnot, which helps you connect multiple layers at once and further helps reduce the resistance in the design. So these things will be taken care as we move to the lower nodes, right? Lower technology nodes, the resistance of the interconnects have started playing a dominant role, which leads to a further slew degradation and addition of further delay, which has become a prominent, challenge for physical design engineers. So I would like to take a stop here, and Sai will take us from here. Thank you.
Thanks, Roshan. So Roshan was talking about from floor planning till routing, right? So as I was mentioning before we kind of hit to the foundry, right? There are a bunch of sign-off checks which needs to be performed, right? And here also the divide by conquer works, like similar to what Roshan mentioned, because the complexities of the SOCs are pretty big, leading to billions of instances, right? So you need to kind of divide and make sure that small partitions or blocks are being met. Then you kind of integrate them and run through some full flat-based analysis to make sure that all the requirements of sign-off is met. To start off with, right, in the sign-off flow, we have the static timing analysis or timing sign-off. You wanted to ensure that a particular product is meeting a performance requirement, right? So the STA does that. So you have PVT corners associated with it. PVT stands for process, voltage, and temperature, right? When you manufacture, what happens is that you don't end up with, because you're manufacturing, these are like very, very small ones, right? So if you're, even if you look at, our regular manufacturing, right? Leo board chip design, you manufacture some water bottle or something like that, right? So there are, the spread, if you take this, let's say each and every water bottle, you take them and then look at the differences in manufacturing, you'll see a little bit of spread or small differences, which you'll see because of manufacturing, error or, such things. Here we are talking about nanometer. We are talking about Armstrong, right? So it's really, really minute. So what happens is that when I say an SS, right, it's not just a dot in the, for manufacturing, it's a spread around that SS corner, right, with variations. That's why we call it SS with global and local variation kind of thing, right? So you don't end up with particular, dot for each and every product. There is a spread of them. So in order to ensure that, we have something called a slow process. We have a typical process and a fast process. What I mean is that's a maximum spread. Typical is what I want always. That's the name. That's the reason why it's called a typical. But sometimes you end up with lots which are a little bit slower because of manufacturing, right? And same, you can also end up with products which are a little bit faster, and if it's called an FF a lot as such, right? So there are specifications. You need to ensure that from a static timing analysis perspective, you are meeting and adhering to a particular frequency performance requirements as such. That is on the setup side, right? So on old, which is independent of the frequency, you want to make sure that old times are all well met, right? So you go to fastest scenarios like, the FF corner to analyze volt, right? You also analyze the SS corner also sometimes because of, the way in which devices and parasitics are there, you might end up with volt even in SS corner also, right? Outlier volts. So you need to ensure all of this is taken care in STA. In addition to that, right, in addition to performance, you have noise, right, which needs to be taken care of. You want to make sure that your noise is well within the limit. Functionally, you could be great. Well, let's say you have a static signal, right? Now, let's say you have a reset, which is there, and suddenly you see a bump on the reset. Your complete functionality is going to change, right? So you want to ensure that noise is taken care of, right? We call it as SNA, static noise analysis, which is also part of the, typically part of the timing sign-off. We also ensure that, various modes are analyzed, right? So we have something called a functional mode. We know that most of the time it's going to operate at this mode. There is also something called a scan mode, right? So effectively, these are like for DFT, right? You want to also make sure that the DFT is working as expected in terms of timing, right? So you run it through in scan mode as well, right? There could also be, high speed modes, low power mode, whatnot, multiple modes, depending upon the product requirements. In addition, you also have, various aspects like aging. You need to margin the design. So you have something called, margining and timing, right? You want to make sure that you account for, some of the IR drop effects, some of the transistor aging effects, right? It's not just a human being who age, right? The transistor also ages over the period of time. That's why you see the cell phone, getting slower over the period of time. Repeated usage of, a switching of a particular gate leads to various reliability aging concerns like HCI, BTI due to kind of trapping of electron into the boundary interfaces as such, right? The oxide interfaces, leading to increased VT, indirectly slowing down the performance of the design as such. So you need to account for all of this, right? Making sure that, let's say you have a product which is there in automobile, you need to ensure that it's working for 10 plus years for sure. For us, probably for a mobile segment, you want to make sure that your EOL probably could be around 3 years or 4 years, right? That's why some of the local mobile manufacturing, you tend to, after 2 years, it looks like really bad, right? So it's, probably it's aged really faster, maybe, right? They didn't account for those uncertainty and margins, right? The power sign off, right? In addition to timing, power is also very, very equally important, right? So people look at timing and they do it, but power is also equally important because of the fact that power is the one which determines the packaging for a particular, design, right? We call it as TDP, thermal dissipated power, right? You design all of them, performance is great, right? Power is skyrocketing, it will lead to, thermal issues, right? And also reliability concerns, right? Thermal stress and whatnot. And it could also lead to thermal runaway or package and drain away and whatnot, right? Due to heat dissipated. So you need to make sure that you're adhering to power spec also. So for this product, there is a power spec which is also being provided. You also wanted to ensure that the power is well within the budget as such. Indirectly, because of the power, consumption is pretty high, and also sometimes, right, group of cells switch simultaneously together, right? We call it a simultaneous switching of cells. What happens is the current in those regions are pretty high, right? We call it the current density in those regions are pretty high, leading to I into R. So resistance of the grid, right? Let's say you have a voltage source which is out there, and from the voltage source, you have basically you have a PCB, you have the package, and you get connected to the bump which is there on a chip, and from the bump as Roshan was mentioning, there is a power mesh to make sure the resistance is less. And from there, it goes and hits through the standard cell rail as such, right? The power rail of the standard cell. So much is a path for resistance which is out there. So when you consume power down underneath, right? So simultaneously, what's going to happen is it's I into R, right? The Ohm's law. So effectively, the voltage which is being provided from the voltage source get attenuated into V minus I into R and reaches to the standard cell, right? Which is much lesser. So you want to make sure that is well within the spec which is maintained. And that's the reason you could see that, let's say a typical voltage is there, you sign off your chip 10% lower than that at SS, which is from the process side, which is very slow. And also from an voltage side, you go 10% lesser than the typical voltage. Let's say your typical voltage is like 0.9 volts, then your, the slow voltage would be 0.81 volts. You want to ensure that the functionality is well maintained there. So that's part of the timing sign off, but on top of that, there are local variations on the grid, which is there. So people have techniques like IR over ST and whatnot to integrate some of these IR drop effects as such. Reliability is a key concern. We have the electro migration, as you would see, right? We have the I average power. You have, unidirectional currents like the power, right? You just keep on, VDD is going to be one directional as such. You wanted to make sure that, it's not catastrophic. Sometimes you have peak EM, that's it. The product is dead. So you wanted to ensure that EM is taken into account, and the EM specification is also material dependent, which is being dictated by the foundry or manufacturing firm, saying that for this metal layer, this much is the maximum current density it could handle, right? So you have tools to kind of analyze them and ensure that EM is taken care of. Various things like time-dependent dielectric breakdown, HCI and BTI, which are on the aging side of it, right, also needs to be considered when you look from a reliability sign-off perspective. In addition to the PV, right, the physical verification is the most important thing, right? And these days it's becoming very, very complex because given that the gate lengths are smaller, the distance between the wires are smaller, chip sizes in general becoming smaller. That means that, the equipments have their own limitations, right? There are new advanced techniques in lithography. You have immersion-based lithography, right, to make sure that numerical aperture is being changed, right? You have patterning-based, multi-pattern-based, technology, because you can't manufacture in one go with, you have to make sure that, there are limitations from, optics side also. You need to ensure that, whatever the blueprint which is being given as layout gets manufactured. So this gets translated into a bunch of rules from the foundry saying that, hey, look at it. These two wires are there. The distance between the wire is, this much. That is called a spacing of it. This is the width of the wire which you need to maintain, right? This is an EOL, end of line spacing. If you have a metal and this is what it is, you need to maintain this kind of spacing. These are the VR spacing. All of this is coming out as a rules from the foundry, and we call it as, design rule check, right? It's typically coded in the DR. It's called as design rule manual, where you have all the rules being outlined for manufacturing. And that gets translated to something called a deck called DRC deck, which foundry provides. And we run through, make sure that we are compliant with all the manufacturing rules, because it has to be manufactured absolutely right. LVS is layout versus schematic. You have designed something which is there on, which is there, but is it really intended on the layout? So we do this check, layout versus schematic check, right, to ensure that both of them are functionally same. There are no shorts, there are no opens, right, and such kind of stuff. Right. And DFM checks, like design for manufacturability. As I told you, these are like very, very, small ones, right? In terms of manufacturing, we're talking about like a nanometer, Armstrong of, length and width of wires and whatnot, right? So design for manufacturability, right, is making sure that, right, you kind of adhere to some of the DFM rules. For example, what happens due to manufacturing, sometimes you might end up with, you create some redundant VRs. For example, you have a space which is there. Roshan was mentioning even for resistance improvement, you can add multi-cut VRs and whatnot. But even from a DFM angle also, right, we kind of add VRs to bolster. Let's say suddenly one of the VRs goes off, some due to some manufacturing or some kind of issues, the other VRs still play a pretty good role as well, right? So DFM also plays very important. So we got these redundant VR checks and some of the lithography, because at the end of the day, these are like optical manufacturing stuff. So you have various effects like line edge roughness, like LER, right? So we do OPC, optical proximity corrections, to ensure that these are being taken care of, right, in terms of pre-layout, which is out there. The post-layout feedback gets into the pre-layout through the foundry with certain set of models which are there. You kind of run through all of these to ensure that you adhere to them. And have better yield as such. CAA stands for critical area analysis. This is like particle defects. Typically, whenever you're manufacturing, these are like very, very close wires. A small particle due to sputter of a copper could short, right, as well. So these are like potential areas. So there are certain topologies. It could be rule-based. It could be model-based. Again, you get from the foundry, if these kind of patterns are there with this much amount of congestion, high probability of, getting particle defect. So you do something called wire spreading. Typically, wire spreading also helps in other avenues like SI prevention and whatnot, but indirectly also helps out on critical area analysis as well, right? Predominantly meant for CAA, right? The next important thing is the logical equivalence check, right? Well, whatever is the logic which is being coded in the RTL is the same as the final netlist which we have, right? It's very, very important because there's so much amount of algorithms involved. Even a small bug, algorithms are at the end of the day, bunch of software, algorithms which have been written through. Let's say due to some bug, right? Suddenly, which shouldn't happen, but let's say some coding at the end of the software one, suddenly a buffer is changed to an inverter. The polarity is completely changed, right? The functionality is going to completely change. So those kind of things have been checked in logical equivalence, making sure the RTL and the layer, the final netlist is all the same. DFT and functional verification, you are ensuring that all the aspects of DFT, right, is being you test upon, right, using all the patterns, all the MBIS patterns, right? You have something called March patterns for the MBIS. Ensure that MBIS is, because memories are really packed in terms of core. You want to make sure that they are being tested properly, and even it's useful for post silicon also, because these are like built-in self-test. When the chip tasks, immediately bunch of patterns gets generated from this built-in self. That's why it's called a built-in. And the memories are being tested. And similarly, there are scannable patterns like, which we have done from this ATPG to get DFT coverage, right? It has also been pushed in post manufacturing just to ensure that, all the testing things are all clean, and it's good for, manufacturing defects. It's clean from a manufacturing defect, and it's good for production as such. So those are the overall, sign-off flows. And as you could see, right, these each and everything individually is like a task by itself. Okay, so you have different set of teams for performing these kind of sign-off flows, right? It's not a one man's job, right? Typically, probably for small blocks, you could do completely from RTL2GDS to including sign-off. But when it comes to integration, so many engineers are involved. So from an opportunistic opportunity perspective, right? If you look at it from a physical design, you have plenty of opportunities, right from full chip, right? If you look at it, there's a dedicated full chip floor planning person, full chip, inside full chip floor planning, who takes care of all the spin cutting and budgeting and whatnot. It's taken care of by the full chip floor planning guy. There's also a full chip clock tree person, right? What is a full chip clock tree? How it needs to be designed for, and how the underneath block owners utilize them, right? There is full chip STA guy, full chip PV guy, full chip IR guy, right? So each and every person, engineer for the full chip perspective. Imagine that you have a chip which is there, which has close to around like 100 partitions or 100 blocks in there. So it's almost like 100 engineers working on various of these, in addition to this full chip person. And you put in the RTL guys who are also looking and designing all of them, probably around like 200, 300 for very big, chips which are there. Overall, for executing a project, you might be looking at close to around like 500, 600 engineers working on it. So the opportunity is plenty, right? And in India, we see that it's been increasingly, there is a lot of increased opportunities on physical design sectors just because of this. So the products have been pretty high, number of products are increasing, and hence the number of physical design, need for physical design people have also been pretty high as such. So before I shift through, right, the left shift, I'm just going to give a glimpse of it because we've over a little bit on the time. If you look at it, the intention here is you look at the sequential steps which are there. How could I make correct by construction? How can I borrow some of the underneath steps, right, below step? For example, you would have mentioned Roshan, if you would observe what Roshan was mentioning on the global route, right? You were saying that's an estimated route during placement, right? How could I make my estimated route same as that of what is seen during routing? If this has not been adhered, optimization would get avoided, right? So basically what's going to happen is this optimization and placement is going to do something else, but the reality is something else. It's called as miscorrelation, right? And basically it's not well correlated. To enable those, right? So we kind of use some of EGR, stands for early global routing, right? Some of these have been borrowed upfront during placement. Same with respect to synthesis. Synthesis is no more just logical transformation. These days, because of increased resistance, synthesis is becoming, physically aware as well. So there are various things like physical aware synthesis, physical aware structuring. You look at really the congestion, then you kind of select logic transformation. You literally look at the logic and then restructure the logic depending upon what the physical needs are, right? So synthesis is also becoming physical aware logical transformation now. It's no more just logical transformation. Same with placement. You build in, typically the flow is to have placement, then do clock tree. What's happening with that is that you don't estimate for some extra buffers which clock tree is going to build in, right? And you might end up with some congestion aspects in placement itself. So borrowing some of the clock tree buffers upfront and estimating them and doing some useful skew optimization upfront is pre-CTS optimized during pre-CTS, right? Is going to help. So all this flows like ECF and whatnot is being done. And same with respect to, routing, we are making sure that it's same as exactly what the sign-off is seeing, right? So you want to make sure the sign-off timer is used, sign-off extractor is used. Sometimes you have this metal fill effect, right? There is some density which needs to be maintained while manufacturing. If you don't maintain that density, you're going to end up with, lifts off and, leading to kind of resistance increase and also manufacturing issues as well, right? So in order to model that, we have virtual metal fill. You're virtually modeling some of them upfront during routing itself to ensure for extra capacitance which gets in. So all of this is the left shift backend flow, and this is predominantly used these days. If you look at it, any of the backend flows right now, it's left shift based. Most of them are being there in order to make sure that we have lesser time to closure as well. So this is a quick recap, right? I'm going to end my presentation with this, and you could see that architecture. I was talking about initially about the architecture portion of it. Architecture is a key. So you have something called PRD, product requirement document, which is get translated to literally the architecture for the product. Architecture, as I told you, is something which is very common, right? And post that, we have microarchitecture, right? So the clear example which I gave you in the front was the x86, which is much more easier to link through. So if you look at it, there is an x86 architecture. Architecture is an x86 architecture, but the microarchitecture implementation between Intel and AMD is quite different, but x86 is the same, right? So that's microarchitecture for you, right? The microarchitecture gets translated to the design, which is, through RTL coding. We have register transfer level logic, which happens, and that gets translated, right? After we do the design, we do verification of the design. You wanted to make sure that, functionally it is all great. By the way, the verification goes all the way till the end, okay? Because it's enormous. You need to make sure that there is enough functional coverage. So the life cycle of verification team is almost till the end. Even after post-silicon also, it sometimes comes out that way, right? So here I'm just talking about pre-silicon, right? And post design has been done. We do all the backend step, synthesis, logic transformation, placement, floor planning, routing, right? Sign-off check. And so all comes under backend, right? That is designed for PD on the left side, which you see. And post that, we kind of hand this over again for verification, which is called back annotated simulations, right? So we have done some design. We have got some, timing also, which is there. You annotate the timing and then do gate level simulation in verification, right? The same also happens in DFT also. You also do an annotated DFT simulation, which also happens, right? In this case also, right, we're doing the verification, right? Because we've been sometimes, right, people don't design complete blocks. So it's also through integration. So each block owners do their own verification. Now, completely when you switch through, right, there could be some interface related verification challenges and issues which would be there. So you could also have some bugs coming out because of that. So that leads to something called ECO cycle, called engineering change order, which gets also, right, as some new incremental design revisions, which happens. Again, the backend team is involved. You kind of roll those ECO changes, again, feed it back to functional verification as such. And at the end, you have, you send this for tapeout. Okay. Does the job end here with GDS2? Absolutely not. So, okay. So there is a lot of things after this. Life after tapeout is also pretty high. Okay. So what happens here, right? So effectively, you would have seen the first slide, right, which was presented to the Sansu, product, right, which is an amazing stuff, by the way. I'm trying to touch upon some of the post-silicon aspect, and there will be subsequent probably webinars which will be covering in detail of this. But if you look at what we are trying to do is once being manufactured, you also wanted to make sure that the manufacturing lot is meeting certain requirements. we do screening of those lot. There is something called wafer acceptance test called VAT, right? So we kind of do test on, wafer level to make sure that, right, everything is all fine in terms of wafer. There are no issues and whatnot, right? And here is where the DFT comes into picture, right? So we also ensure that after we do that, we kind of cut through those into multiple dies which are there. You do verification using the DFT things which we add, right? All of the stimulus to ensure that everything is all clean from a manufacturing perspective. There are no any manufacturing defects as such, right? In addition to that, we also screen this particular, as I told you, the manufacturing is not just a dot. You don't get always a dot in manufacturing. What I mean is it's not exactly typical process. You end up with SS process. You might end up with FF process. This process of segregating, you take particular die and you keep on segregating which process it belongs to, right? Whether it's a soap process or a typical process or phosphate, it's called binning, right? And people also use this concept for, sometimes you want to run certain chips for very high performance, like let's say a CPU, just you can sell those products also on a higher price as well, right? Let's say you got an FF lot, which is there. You could, you can have high performance for that particular chip. You could also have, sell those products for higher prices as well. This is called a speed binning, which happens. After we have these kind of dies which have been diced, so you kind of make sure that, all of the packaging which is being taken care of, packaging is very challenging these days. Okay, so because of the thermal requirements which are out there, so you could see literally, a bunch of various packaging ways of doing packaging to make sure that the heat is being dissipated much better as such, right? Typical ones which have been reading in the schools are using heat sinks as such, right? But there could also be some of the liquid coolants which would go through all the, to ensure that, heat is dissipated much better. Board design, right? So after the package is there, you kind of have this onto the board, and you assemble and you get the board, and then you do silicon bring up, right? So if there are any issues, completely integrating and making sure that everything is all clean. And post, right, again, you pump in some vectors, make sure that all the boards, everything is, board traces are also clean and whatnot. Then you do complete silicon testing. So why am I saying all of this, right? So when we are doing these kind of, testing post silicon, there could be bugs which could be there. So it involves all the way from, logic guys, there is backend guys who have been involved to investigate layouts, timing issues, timing guys are involved, IR issues, IR guys are involved, DFT. So all of them, right? So basically it's like mostly looking and unraveling what kind of issue is it, and corresponding segment of people are being roped in to do this, right? Hence I was saying, right, the post silicon put together, as you could see, it's like a synergy of so many engineers working on to get the chip up and working, right? We see the final product, but so much brains behind it, so much amount of effort, right? So many engineers behind this, right? And there's a lot of requirement, right? As I told you, in physical design world as such. With this, I conclude my presentation and open up for any of the Q&A. And again, I thank, IESA for providing this opportunity for presenting.
Thank you, Sai. Thank you, Roshan, for giving us such an informative session. So maybe to end, we can have two things to you guys, where you can just share some lights. That if, like, from a new engineer point of view, or from someone who is aspiring to be engineer in this physical design domain, or so, what are some common mistakes that they may make while they are learning this RTL2GDS flow, and how it can be avoided?
Okay. So typically, right, so if you look at the textbooks for RTL2, GDS2, right, now there's been a lot of improvements out there, right? Typically we study that as a very a couple of pages out there, and unfortunately or fortunately, that's the life of a physical design engineer, where that particular 2-page gets blown up into very big broad spectrum. So what happens is that people typically, they get lost when they come to this EDA tool usage space. Electronic people typically, they are more glued on to some of the electronic circuit concept, and some of these also involves a little bit of more scripting, more software, a little bit on software side, on the scripting side. So what happens is that they said, oh, I'm an electronic engineer, so should I touch upon these scripting? And they sometimes, right, the mindset is what it is, right? And they kind of lose a little bit track out there. So if they could, as part of the curriculum nowadays, I guess most of the, institutes also have tickle coding, right? A tool command language, which is out there. Some of the codings, some of the tools are also moving towards Python these days, given the wide usage, but mostly predominantly tickle. So once you have this tickle knowledge, automation mindset in your thinking, and also this physical design, to be honest, it's, as Roshan was mentioning, right? It's looking at details of the data flow, and then you are designing for, you understand the design and then design through. So you need a lot of insights on some of the logic, computer architecture, microarchitecture, and whatnot. And physical design will become like a breeze if you have solid background on some of these, right? Just doing physical design, you could do it, but having knowledge of microarchitecture, understanding, the impact of microarchitecture on, what's happening in physical design world, right, would add a lot of values. And patience is a key, right? Obviously, it will take time, right, to become a physical design engineer. What you read in school, right, would be a little bit different from what you see in practicality. You will see congestion and blocks. You will see some different, Roshan was showing a squarish floor plan, but in reality, you could see floor plans which are really, really hard, and which leads to congestion, timing closure, and whatnot. I'm sure that which patients, right, which you have patients with amount of prerequisites which are out there, we should be able to crack. It'll be very easier for anyone to come to physical design field and pursue that as a career.
So I think thank you for sharing this. Maybe your like 2 words of advice from both of you to the future generations who will be good, who are aspiring to become a good physical design engineer or engineer in the related fields. So 2 words of advice from you both for them.
Roshan, you want to go first?
One thing is very important. I think it's very important to have a liking for something. So if you're really interested in engineering world, whatever field it be, whether it is physical design, whether it is the design of the RTL itself or architecture, you should figure out what your interest is. If you know what your interest is, whatever be the consequences, however the path is, you will learn. You will make it out. So it's very important for you or for me as an engineer to figure out what my interests are and pursue your interest. There could be challenges. That's fine, but you'll be able to cross those challenges. Yeah.
Thank you, Roshan.
Yeah, I guess I completely, concur what Roshan is saying, right? It's about passion, right? So passion for doing things, right? If you have the passion, physical design, as I told you, it's just a passion thing, actually. So each and every day in physical design world, which we have internal to our organization, right, we kind of constantly innovate. And as I told you, as physical design, not just about automatic place and route as such. Okay, there are other avenues which I told you, right? It could be analog layout, right? Someone could be really passionate. You know the design of the analog, also do layout of that. Back look at what is the impact on analog design, right? That's also very, very interesting. So there are various avenues in physical design also. And as I told you, physical design is not just one all the way from RTL to GDS2. There are focused avenues looking at, packaging impact on physical design, looking at, pump placement on physical design, all of this, right? So it's physical design is like bunch of, you'll get a very big breadth of items in physical design and it's just about passion towards it. It's not just using just the tools, right? You have a lot of things to do in physical design as such, and it's just about passion and resilience, right? So basically, you need to pick. Surely you'll be lost at some point of time, right? Everyone would have gone through that. It's just getting up and then going for further, right? So and you'll enjoy for sure, right? That's that the drop down and you get up and then you go further and you see something coming up. That's where the excitement and enjoyment is. That's what Roshan was clearly mentioning, right? You should have interest towards this. If you don't have interest, you'll probably bog down. But if you have interest, you'll surely go for it further.
So I think with this, on behalf of all our viewers, I'll thank you both for taking out your time and sharing this informative session with all of us. And also I thank all of our viewers to join us. So thank you, Roshan. Thank you, Sai.
Thank you
Thank you.
very much.